This topic is energy, power and climate change. First we look at energy degradation and power generation. We will look at 4 points. Some energy must be lost to the system, about degraded energy, energy flow diagrams and electrical power production. You have to state that thermal energy may be completely converted into work in a single process, but this continuous conversion of energy into work requires a cyclical process and the transfer of some energy from the system. So we have a piston, we have a volume of air in here which is inside this piston. We're going to heat this piston, we're going to heat this cylinder of air, so it's going to heat up and it's going to expand. So in expanding it does work to the surroundings. However, we want to keep on doing the work and the cylinder is not going to expand forever, so we need to get the cylinder to go back again. How do we make the cylinder go back again? Well, already it's been heated up, so we have to cool it down again to make the cylinder go back. So we take the heat away from it. That's the only way we can make the cylinder contract to its original size. But to remove the energy, we have to degrade it. We have to throw it out into the surroundings, and then when it spreads out, it becomes degraded. So we can get heat to do work, but in doing that, for a cyclical process, we must throw some of the heat away. So we have a heat engine. This is a heat engine. So some of the heat goes into the body, into the heat engine, and then it's able to do some work. However, it will not continue doing work, because if we want to continue, we have to throw some heat out to a cold body. So the energy in, the thermal energy in, some is converted into work, but some has to go to a cold body. Some has to be thrown away. A steam engine, for example, the coal is burned to give heat to the engine so that it may do some work, but it has to throw the energy away, and it has to throw it to a cooler body, the surroundings. However, if Thomas is in hell, there's not a chance in hell that he will be able to move, because when the heat gets thrown out to the surroundings, heat will not move out to the surroundings because it is already hot in hell. So there's nowhere for the heat to go. So Thomas will not work in hell. Once he's there, he stays there. Explain what is meant by degraded energy. This is when wasted energy spreads out into the surroundings and it's dissipated. It spreads out into the environment. This dissipated energy is too spread out to be able to do any more useful work. It cannot be reused. It's too spread out. It becomes degraded. It's still there, but it's too spread out. So this is why it's important to reduce the amount of energy that is wasted, because when it gets wasted, when it gets degraded, it can't be used again. We have to be able to construct and analyse Sankey diagrams. So, 3 main features of a Sankey diagram. The first one is the useful energy moves from left to right. Second point, wasted energy on the journey moves up or down and does not go to the right. Third point, the width of the arrows in the Sankey diagram show the proportions of the energy. Here we have an example. Energy goes from left to right. This is the useful energy output, which is the light energy from a light bulb. Some energy is lost from heat as heat and moves upwards. You can say by looking at this Sankey diagram that roughly 40% of the energy is turned into light, roughly 60% is turned into heat. So this is effectively a 40% efficient light bulb. Here's another Sankey diagram here. For every 100 joules of fuel that go into a power station, there are 20 joules that are lost to start with when it's heated, when it's burned. When the steam is used, it must be cooled to cool it down. That loses another 40 joules. In the generator, there is 5 joules of energy lost. So the only useful energy is basically 35 joules. But notice that the width at different parts represent the amount of energy. So you're left with 35 joules out of 100 joules, so this is only 35% efficient, this power station. The main parts involved in the production of electrical power. So we basically need to get electrical energy. To get electrical energy, you have kinetic energy. The turbine is moving, or the dynamo is moving. This is turned by a generator into electrical energy. This happens in most forms of energy generation. We have nuclear energy, solar energy, and chemical energy. This produces heat energy directly. This heat energy basically heats steam. The steam drives the turbine, makes it spin round, and this is kinetic energy, and then turns into electrical energy. So the nuclear energy, solar energy, and chemical energy, this is how these work. On the other hand, sometimes you have hydroelectric, waves, or wind. These are already kinetic energy, so there's no heating that needs to take place. These are already kinetic energy in these forms. They turn into the kinetic energy of the turbine, which turns into electrical energy. Here, for example, we have a thermal power station. We have the boiler, the turbine, the generator, and the transformer, and the cooling tower, of course. So a thermal power station uses heat to generate electricity. Heat engines are not very efficient because we have to throw away a lot of the heat to the cooling tower. So what does each part do? The boiler takes the fuel, which is chemical energy, turns it into heat energy. The turbine takes the heat energy, which is basically kinetic energy, it's the steam, and turns it into the kinetic energy. It makes the turbine spin round. Then the generator changes this kinetic energy into electrical energy. And of course, this is not an essential part of the energy conversion, but it's important to be able to remove some of the thermal energy to make this run faster.